And I'll explain how I'm going to refer to things so we're all working the same way. Whenever you're trying to figure out the value of a logarithm, basically you're going to take the log and you're going to turn it into what's called its exponential form. Okay, so this would be my log form, and this would be my exponential form. So if you're asked to go from one to the other, you know what the heck, they're talking about. And basically, what you're doing is you're looking at this, and your sub-base, your little b down here, is going to become the base of your exponent over here. That'll always be the same. Whatever your solution is in your logarithm will always be your exponent, and then your regular base, your big base, I like to call it, because it's a bigger variable here, ends up being your answer. So here's how this works. Let's scooch that just a little. So here, if I'm rewriting it, my sub-base becomes the base of my equation. My answer becomes my exponent, and my big base becomes that. Now for this part, I'm just concerning myself with rewriting. I'm not trying to solve anything yet. Okay? I just want you to get used to how this kind of sets up and works. But it always is going to be the same. Base, exponent, answer. Oh, 5 to the 0 power is 1. Okay, that makes sense. So you'll get true statements with these as you fill them in. So when I come over to here, okay, what's this one going to look like? 10 to the first power equals 10. That's true. Then the last one may seem a little odd. You're like, 10 to the negative first equals 0.1. What? What's 0.1 as a fraction? 1/10. So that makes sense. Okay, I could put the 0.1 here, but what's the negative exponent do? It means I take this, which would be like 10 over 1, I take its reciprocal. I flip it. So 10 to the negative 1 would be 1/10, or 0.1. Still a true statement. And that's something we'll have to get used to a little bit. But even as we keep working them, as long as you get the general format, base, exponent, answer, if I take 1/2 and flip it, what do I get? 2 over 1, or 2. And that's the type of thing that we're looking for here. But then, of course, it has to go and start to get a little more abstract. You're like, well, what if I just have this part and I don't put anything over here? What if that was the whole problem? You know, how would I set that up? Anytime that you don't have something on your equals or on your solution type side, I'm going to replace that with an x. Because then if I want to figure out what that value is, I can. So it's still base, exponent, answer. Now, let's say I wanted to make this a true statement. I wanted to figure out an x value that would make this true. You're like, I can take b to some power and just get 1? What can you take, what certain number can you use here for the exponent that'll always make this equal 1? 0. Okay? Since b to the 0 power would be 1, my x value, okay, could be 0 here. So we'll get to a point where it does become a puzzle. We take the form, and now we can start figuring out x values. Now, they won't always be abstract like this, but it's good to see some of these. What's this equation going to look like? Yeah, b to the x, base, exponent, answer. What power do you take something to if you want to get it back? 1. Because anything to the first power gets it back. B to the first power is b. Okay? But the big thing right now is just understanding that when you go to write it, sub-base, there's my exponent, there's my answer. Because when I start getting into actually figuring out numbers like I do here, again, if I don't have that equals in something there, I'm just going to use x to let me think about it. So this would be 3 to the x equals 81. Now there's going to be some mental math involved in this. You're not going to get like decimal answers and things like that. Okay? Right. Because here, x is going to be 4. You're like, how the heck are you getting that? Because I've got to figure out 3 to what power is going to be 81. Now if that means here at the start that I just have to play with some numbers until I get there. So let's say I'm like, I don't know, what about 3 to the third? Nope, that's too small. What about 3 to the fourth? Oh, there's the 81. Okay. Play with it a little bit. Now on this next one, there's a little more to think about. Okay, what would the equation look like on 9? Five to the x equals 0.04. You're like, well, what the? Okay, let's simplify some things. Do you know what 0.04 as a fraction would be? If not, take that decimal, put it in and hit math, enter, enter, which is 1/25, okay? So now, let's think about this for a second. 5 to what power gets me to 25? 2. But what do I need to do to that exponent? So I need to flip it. Use a negative exponent. So, one thing I might be able to take on here is a generality when I'm trying to do this that I might want to make a note of here. We'll get a couple of special cases. If I need to do a fraction flip, in other words, I go from a whole number to a fraction, or vice versa, I'm going to have a negative exponent involved. That's going to be part of what my answer is going to be. So if for some reason I have a fraction, I go to a whole number sometime, that same thing is going to happen. So let's see here. What's my equation in 10 going to look like? 1/2 to the x equals 8. Now I know a couple of things here. First thing I noticed is, 2 to what power gets me to 8? 3. And I'm going from fraction to whole number. That's the same thing as going whole number to fraction, which means I have to get a negative exponent in there. Okay? Fraction to whole to fraction, have to have a negative. But notice I'm not worrying about that at the start. I'm just looking to see, what do I take this whole number power by to get to here? We did 5 to get to 25 is 2. 2 to get to 8 is 3. And then I start dealing with the negative part. So that's one thing to keep in mind. The other thing that can kind of mess with me, 9 to the x equals 3. What? Well, I know it's not a negative exponent because it didn't go to a fraction. What can I do here? An exponent with 9 to get to 3. Let's see here. Oh. Now you're like, now where would in the daylights would I come up with 1/2? Well, let's think about this for a minute. The square root of 9 is 3. Okay? So if I'm looking at this and I say, okay, the square root of 9 is 3, how can I write square root as an exponent, taking it to the 1/2 power? So here's our other note that we want to make when we're looking at this section. Okay, we'll kind of call this number 2 here. The first one says if I see a fraction flip, so I go from like a whole number to a fraction, I'm going to have a negative exponent. Here, if I have a smaller value, now what I mean by that is my base 9 is bigger than the answer 3, or like if I had 16 and 4, or 8 and 2, or something like that, okay? That means I'm more than likely going to be taking a square root of something. So I'd have something to the 1/2 power. Usually we don't get into cubes and stuff like that here. That gets a little over the top. But being able to look at these and do some mental math or play on the calculator a little bit, a lot of our problems will be like 8. They'll be whole number answers. But I wanted you to be really aware, if you go from a whole number to a fraction or a fraction to a whole number, it's a negative exponent. If you go from a bigger number to a smaller one, typically that's going to be some sort of a square root, unless there's a fraction involved. But it's one of those things that as you get more used to it, it'll get a little bit better. But are we okay on the setup right now? I know some of the mental math is going to get to be tricky here as you start to get used to it. Okay. So, using some regular logs. Okay. A log, when you type in log on your calculator, it's assumed that it's what's called a base 10 if you don't see anything. So for instance here, if I've got log 5, I'm just going to punch that in the calculator. There's nothing fancy to do here. So I can just go to the calculator and hit log 5, enter. And I'll get some funky decimal. Typically we're going to go to 3 decimal places on these. So like in this case, 3 decimal places would be 0.699. And there'll be some uses for things like this in the future, which is why we're just kind of playing with it a bit. The biggest thing here is playing with the rounding involved. So as I punch those in, I just want to make sure that I'm making sure I'm getting the same answer. Now notice on this one, I forgot to close my parentheses. It still worked for me. As long as there's not something else going on there, I can get away with that. But it's not something I want to get in a habit of. And then if you get asked for natural log, you just go to the button right below log. Okay, ln. Put that 0.2. You can get negatives, you can get positives. Whoops, move that over so we can see a little better. But everything is just like anything else, whether it's, a new pair of shoes, a video game, whatever it happens to be. The more you play around with it, the more comfortable you're going to get. And so you're like, okay, that's not bad. So what we're going to do, I'm going to go past 16 for right now, because I want to kind of hammer this part down that we're doing here. Let's put this up here for a second. Now, inverse properties. Here's something that's kind of cool, which you're going to come in real handy. Because like when you do equations, if you're multiplying something, you do the opposite, it's divide. If you have a square root, you do the opposite, squared. There's a couple of opposites with inverses that I need to make you aware of. The first one is any base and its log cancel each other. And I'll put cancel in quotations here because mathematically speaking, they're inverses, but understanding the word cancel is a little bit better. So like for instance, bless you. When you're looking at 17, this is the prime example of our first rule. Log base 6 of 6. A log and its base are inverses, and in this case, all that's left is the exponent. And we'll be doing some manipulating so this happens ourselves. And it also works that same way like on 18. The base can be here and the log can be in the exponent. Same idea though. A log and its base are inverses. The exponents, all we have left is the answer. The other inverse property is the one I mentioned a little bit back on Monday when we talked about E. E and natural log are inverses or cancel each other. So if I have E and ln, okay, just use the 15. And then you're going to get a little bit of an intro. Because you're like, well, now what's going on here? Because that 2's in the way. How does this work? Let me give you a little intro of what we're going to get into here in a couple of days. When we get into what's calling condensing laws, this little 2 is going to swing up here. So this is what this would look like. We're going to be able to manipulate this so I can get the e and the ln together, so they can be inverses. And 3 squared equals 9. But this is kind of a future reference example. Okay? So if you ever need to get at ln or get it closer where you can actually cancel them out, that's an option that we're going to have if there's a coefficient in the way. Like I said, a little more for future reference. The rest of them all are going to be pretty straightforward, though. Here, my ln and my e would cancel, and I multiply what's left. So this is just 5 times 3. And some of you may say, well, could I type this in on the calculator for some of this and get the same thing if I wasn't sure? Yep. So like, let's say that one we just did. I type in 5 ln, second here. I can get the same answer. So if you're ever not sure, there are ways to double check on a lot of these. Here I've got to remember, oh yeah, if I just see the word log, that's really log base 10, like we saw up above. A log and its base are opposite, they're inverses, and I'm good. And then you're like, ooh. Now this is different because, well, that 9, that's not 3, so they can't cancel. Ooh, but the 9 is in disguise. Now we get to be detectives. What's another way I could write 9, but give it a base of 3 so I could work with it? 3 to what power gets me to 9? 2. So sometimes I may have to take the base they give me and tweak it a little, because now by turning that into 3 squared, which is still 9, those can cancel, and I multiply what's left. It's kind of cool. I mean, you get to start messing with these things and basically turn them into what you'd like them to be. Not too bad of a deal. But again, that's one that we'll do a little more as we move on, but I always have to have that base and my subbase the same so I can cancel those. So I may have to make a little bit of a conversion at times. Right? So, as I flip over, like, oh, we see the graph coming. Okay? Inverses, just like we've always been doing on any inverse. Switch x and y first, solve for y. No different than when we were doing this before. The only difference is now there's logarithms involved. So the way that we go about solving might change a little bit. So my first job is to switch the x and y around, but now I'm solving for y. You're like, well, get rid of log 3. What's up with that? Okay, let's think for a second. I go back and look over here. I'm like, oh, so when I had a log of something, if I had the big number, I can make this work. Watch this trick. If I want to get rid of log 3, I need a base 3 to work with. So here's how this works, and I'll write it this way for the first one. I'm going to turn the actual equation parts of this into exponents. That's one property of logarithms I can use. I'm doing the same thing to both sides. I'm making both sides an exponent with a base of 3. But on this side, 3 and the base log of 3 are the same. I get y on a side by itself. The other side is 3 to the x. And that's my inverse. And it'll work that way every time with these. So like here, my big thing is, I've got to remind myself, if I don't see a number for my log, that it's a 10. It's always going to be base 10. So if I need to get rid of log base 10, once I switch my x and my y, I'm going to turn both sides into exponents again. So since I need it to be base 10, I put a 10 here to turn those into my exponentials. My log base 10 and my 10 are inverses. And I've got the answer. Some of you are starting to look at this and go, oh, so basically it's just whatever my subbase is to the x. Basically, when you're looking at a regular logarithm, it will be. When it's natural log, oops, that's a y. Same idea is going to work here, except what's my inverse of natural log? E. Still going to use the exponent idea, but I'm going to use E as my base now. So my E and my natural log will cancel. And I have one step left this time to get y alone, and that's to subtract the 1. But I can continue to keep making my size exponents by using either the base of my log or E as an inverse. And then the graphing, we are going to keep life simple. The graphing is going to have a lot of similarities to what we just got done with, except a couple of things that you will notice. Now let me pop this first one up. Yeah, we're going to start busting out the word asymptote here. Some of you may just want to call it totes because you're going to giggle too much saying the whole thing. So, when I go to graph this one, that's kind of weird. Basically, what we're doing here is, before what would happen, actually I don't have to, yeah I do. If we had something that was growth or decay before, it would come from up top and from the bottom, and it would hug the x-axis. So technically I had a horizontal asymptote last section. Now, this one, even though I can't see it, this is going to hug the y-axis, which is going to give me what's called a vertical asymptote. So, on this particular one, my vertical asymptote is going to be where x equals 0. There's this imaginary line going along here, and sometimes I draw it just to remind myself. My graph can't go through there. That's the do not cross line. So when I go to graph this, let me get myself some values so I can make this work a little. And you'll start seeing the word error. Again, that's where my asymptote's at that it can't cross. So I start looking at these. I'm like, okay, so 1, 0. All right, that's a point. And you notice the values are going up really, really small. I mean, I'm up to 6 here, and I'm not even to 1 yet. What I normally try to do is see if I can find one more value that's a whole number, and then use that as my key. So when I go to graph it now, yep, I got arrows going on both ends of this, but I'm really, really, really hugging that asymptote right up against it, but I'm not crossing it. X-intercepts, typically on these, unless you have some shift, are going to be at 1, 0. But we're not going to concern ourselves as much with the intercepts in this section because this can get a little more complex at times. So for now, we'll just kind of leave that one at that. Transformations, okay? Fancy words for shifts. Let me tell you how those are going to work before we actually get into some of them here. If it's inside the parentheses, sort of like it would be if you look down at number 28, those are going to be my left and right shifts. And just like they were before, they're the ones that are opposite of what you would think. If it's plus, I'm going to shift left. If it's minus, I'm going to shift right. Because the actual form is x minus h. If It's like 29, where the plus or minus is outside of the parentheses. That's going to be my up or down shift. Up being up, down being minus. Okay? So we can have an idea of where the graph should be going before we start doing it. And then the last part, with domain and range, it's going to be the exact opposite of what we were doing with growth and decay. Now, my range is going to be the one that's going to be going from negative to positive infinity all the time instead of the domain. And then here in this case, right, my domain, my x values, if their leftmost point are at 0, 0, 0, and heading off to infinity. So just to make one little extra helpful note here, if your asymptote moves left or right, your domain will move with it. Whatever your asymptote value is to infinity is what your domain's going to be. So like here, my vertical asymptote was at 0, so then my domain goes from 0 to infinity. If my vertical asymptote was at -3, my domain would be -3 to infinity. Those things are going to go hand in hand. So I should be able to figure out a lot of this information just from seeing the equation, not necessarily thinking I have to, do everything on the calculator. So for instance, when I get down below to those different types of equations. Now sure, I'm going to go ahead, I'm going to plunge things in on the calculator to help me out with some things. I mean, it'd be silly not to. But when I get here, I should be able to figure out a few things. First thing, what shift does that represent, that +1? Okay, left one. So again, when it's in the parentheses, it's going to be the opposite of what we might necessarily think. So that should tell me a little bit about my asymptote. So if I do my log, oops, I always forget they give me that without me even doing it. Make sure you get your parenthesis closed up, because I want it in the parenthesis with. And I graph, notice what happens. It's now finishing over at -1, because my whole graph is shifted left 1. If I look at my chart, okay, I now have a value at 0, but I get an error at -1, which is kind of my hint on where my asymptote might be. So again, I'm just going to draw it in so I know where it's at. So my asymptote is that x equals -1. It's shifted left 1. The only time my asymptote moves is left or right, which also means my domain is going to shift to the left, right along with it. My range never changes. So you notice I'm getting all this info. I really wouldn't have even had to look at the graph. My vertical asymptote, my VA, yeah, my vertical asymptote, yeah, not my intercept. And in this case, I can easily find my x-intercept. It's at 0, 0. Now again, if you want to make your graph just by popping some of these random values in, you can. I, again, usually like to look for something with a whole number. I see there's one at 9, 1. I connect the dots, and I'm good. So there's not a whole lot of weird things going on here. What type of shift is there in 29? Okay, up 4. Now, is that going to mess with my asymptote at all? No. Asymptotes only get messed with on the left or right. So my domain still is going to be 0 to infinity. My range is still going to be -infinity to infinity. Since it didn't shift left or right, my vertical asymptote isn't going to move. So when I go to graph here, when I type this one in, I've got to make sure I close my parenthesis before I do the +4, because otherwise I'll get a left shift instead of up. So I start to look, and I'm like, okay, I got to point at 1, 4. I know my asymptote is at 0, so we're not going to cross 0. See if I can get any other info here that's nice. Okay, and I see that the value at 10 is going to be 5, to give me a little more accuracy here. Now this one, you'll notice the x-intercept. We're going to leave that alone for right now. Life is going to start getting trickier on finding these intercepts. We'll get into that. That's a little bit for later because we don't want to go too much at once. So I'm going to leave that for right now. So I want to get this last one in. And then we'll get some more flex time here moving forward. All right, what are my ifs on 30? Right 2, down 3. So what's that going to do to my domain? Because now that left-right shift is going to make movement. That right 2 shift is going to move my domain right 2. So I look, I'm like, ooh, 2 is where the error starts. So 2 to infinity would be my domain. Range still ain't going to change. And like I said before, your vertical asymptote and your domain go hand in hand. Because that's where my wall is, so I can get my values. So I've got 3, -3. I don't know if I'm going to get any other good ones. 12 is -2. Okay, I'll come out here a little ways. And then I just say, okay, is that going to make this look accurate? It is. Down. And I'm good. And on this one, your x-intercept, if you went looking for it, would be ridiculous. Because it's at 1,000. I'm like, why do I want to go to 1,000? I wouldn't know either. But I'm not going to worry about it. So what will happen on a lot of these problems? Okay? There is hardly any length to any of these. Because you'll look at the ones I've got up here, you're like, holy cow, Hardy. That's like 8 gazillion problems. What happens is, on all of them except basically the last 3, is what you have seen here on the front, where you're making one quick calculation, is what those problems are going to be. So the assignment itself, I'll put it here too. I think I can squeeze it in, especially if I wipe the calculator out here. The last 3 problems, you're asked to graph the logarithm. And I just want you to find the domain, the range, and the end behavior. But when you're drawing them, draw the asymptote on your graph, because I want you to keep that in your head of how those things are connecting, your asymptote and your domain on those. And then tomorrow we'll start to bring in this whole condense, expand thing, and actually get into more of the fun of it, more than just graphing some of these things. And then, yes, we will get into a workday quicker on this unit than we have before. These first 2 days, and then we'll kind of step back some. So by Friday, we'll be in the workday mode to kind of see how things are going with that. But again, this whole assignment, basically, except those last 3, if you even had just a basic old standard scientific calculator, there's logarithm buttons on them. Even on my little dollar cheapy one here, I think I have a logarithm button. Yeah. And then again, if you're having issues or you have questions on the quiz or missed the quiz or anything like that, I'll be here after till about 4:30. So if you want to drop in, feel free. I'll be here in the morning again. So most of you are off to a good start on here. Oh my gosh, I haven't hit stop.